Welcome back to DevOps Prof Conference 2022. I'm Kevin Jacob, your host. I'm a DevOps consultant at FE Code, and today we have Ed Shee, Head of Developer Relations at Selden. Uh, Ed would be talking about tackling the massive complexity of production, machine learning, and MLOps being the hot topic right now. I'm sure all of us is going to enjoy this session and learn a lot from you, Ed. Over to you. Over to you. Please go ahead and share your screen right now so that I can confirm that screen is.
Okay, yeah, let's do it.
Meanwhile, make sure to use the Q&A section, and please make sure to upvote the questions that you think needs to be taken first. Ed, your screen is visible and your audio is good. We're ready to go.
Cool, great. Thank you very much, Kevin. So yeah, hi everyone. Nice to be here. I hope you're all enjoying the conference. I've been loving it, listening to some of the talks over the last couple of days. So yeah, as Kevin mentioned, I'm going to talk about tackling the massive complexity of production machine learning, which is quite a mouthful, right, in terms of a title. But yeah, you could distill it down to the word of MLOps, right, which seems to be the buzzword that has kind of taken off in that space. So if you haven't heard of MLOps before, it's just like a shortening of machine learning and operations, a bit like DevOps is. And it gives us like a nice umbrella to talk about all of the processes, the tools, the kind of culture shift that needs to go on, moving data scientists from experimentation to production. And that's a lot of what I'm going to talk about today. So quick little thing about me. So there's a picture of me playing lacrosse there. I don't know if I guess in Europe, I don't get much love for that. But over in North America, people are like, wow, there's a guy from Britain who plays lacrosse. So yeah, it's something about me. I also love pizza. And I've spent probably, well, it's actually now closer to 10 years doing software delivery lifecycle, DevOps, and cloud architecture roles. But I've always had this kind of fascination by AI and machine learning. I did a degree in mechanical engineering actually, and did a lot of computational modeling and matrix multiplication and so on. And so when I started digging into the math side of things, I was like, oh, hey, this is really familiar to me. I really enjoyed it. And I liked, building neural networks from scratch and stuff like that. So I had this kind of passion for it. And then over the last kind of couple of years have now transitioned into more of an MLOps practitioner role. And what I currently do is I head up developer relations, or DevRel as the cool kids call it, at a company called Selden. And what Selden do is provide tooling for machine learning deployment, management of models, explainability, monitoring, things like that. I like to call it the last mile of machine learning. So kind of, once you've got a trained model, how do you actually get that to run at scale? So it's kind of DevOps meets machine learning. And I found, there's been this baptism of fire, right, being thrown into suddenly doing, production machine learning at scale. And that's kind of what I'm going to talk about today is, some of the things I've learned along the way. Let me just hide that. Cool. Oh, okay. So kind of the motivation for this is that the way that we do data science generally goes against agile principles. If you think about, the way that software engineering now has very much embraced agile, a lot of those things are still kind of new concepts to data scientists. So let's look at some of these issues. So the first is that a lot of the work is done in complete isolation. There's, rarely is a model trained or built by a team, even if they might have input towards it. It's normally an individual practitioner actually designs the model architecture and does the training. And all of it's very experimentation driven. People tend to try a bunch of different parameters, see how it works out, run another couple of experiments, create a bunch of new code and just see how it works, manipulate the data a bit more. There's a lot of trial and error in the way that it's done. another thing that data scientists do is they get very hung up on like model accuracy or some other metric and spend weeks or even months trying to optimize their model to get fractional improvements in the, let's say your model's like 90% accurate. You might spend weeks getting it to like 92% accuracy, which is still a huge jump, and maybe there's a certain number you need to get to be able to deploy it. But all of that time, right? If you think about the agile methodology, all of that time is stuff that is time that you don't have the model being used in the hands of users, getting feedback on it, trying to gather real live data from the deployments. So there's kind of this mismatch there. And then from my experience, there tends to be a complete lack of testing. People don't test the code. There's very little testing done on data and data sets and so on. So very immature, right, in that space. And what's typically happened, right, is companies have gone, oh, we need to do AI, right? If you're a kind of middle of the road, let's say insurance company, you're like, well, we can't not do machine learning and AI, right? Everyone's doing it. So you hire a bunch of data scientists, and that's, you probably did a few years ago. And they've now got to the point where they've built some cool models, and they can showcase like, hey, look, we can really accurately predict what our revenue is going to be next quarter, or how many claims we're going to get for a certain month. And this is very useful, but companies are now saying like, okay, that's cool that you can show me that in a report or whatever, but I want to be able to do stuff with it programmatically. I need to be able to actually, embed it into my business processes and systems to be able to really generate value from those machine learning models. And that's often where like a lot of companies are now at, is, they've established like building and training models. That bit they've got good at, and they've got a team for that. But how do they embed them into the processes and get them running at scale is the challenge. Okay, let's talk about Jupyter Notebooks. So if you're not familiar with Jupyter Notebooks, these are essentially like it's like a sort of Python IDE, right? You write code, but what's really nice about it is that you can write code, and you can also write Markdown, and you can execute those cells, right, as and when you like. So you can jump around the notebook. I can run a code snippet up here, and then I can jump down here and run another code snippet. And all of the outputs are visualized and stored within the notebook. So they're very good for experimentation. I actually talked about some of these already. The problem with Jupyter Notebooks is that in theory, they're supposed to be reproducible, right? I can say, here's a notebook I wrote. You can see all the outputs, the code in there. I can send it over to you, and you can step through the code. You can step through each cell, and in theory, it should run. But they're only reproducible to the point of the actual code inside it. It doesn't contain any awareness of the actual version of Python that's being used to run the notebook, or the dependencies that are being used. So they're a bit of a mess, right? And typically data scientists use Jupyter Notebooks for everything. And if you're interested and you have data scientists working in that way, Google wrote a bunch of like notebook best practices, which get you some of the way towards being able to write Jupyter Notebooks in a way that you can then take the code afterwards and get it into a scalable and deployable unit. Because obviously, if you're a DevOps engineer and someone goes, oh yeah, here's my IPython notebook, please deploy it, you're going to go like, what on earth am I supposed to do with this, right? It's not really a deployable asset. Okay, so assuming you've got over some of those hurdles, right? You've trained a model, you've followed some, let's say you're even a beginner in the machine learning space, and you've followed some tutorials online, you train a model, great. Now it's time to deploy it. So the typical like solution that you would go after is to say, well, right, if I need to make predictions and I want this as an API, why don't I just wrap it in something like Flask, right? And there's that's actually a very valid approach, right? It's a Python model. Just create a REST API, and then job done. Okay, so and you can see with this code sample on the right hand side, just within what's that, maybe like 20 lines of code, 25 lines of code. You could have a, a slash predict route. It could import your model. It can, run a prediction and then return that back to the user. So that's now pretty usable, right? I can get the rest of my business and software engineers to do it. There's actually nothing wrong with this approach, and it's one I recommend people do if they need to get something out there quickly. And maybe even for some models, it's the end solution. But there are also a lot of issues and a lot of problems. So yeah, success, like model deployed, but now let's look at, how things suddenly become really quite difficult, particularly if you just wrap it in something like Flask and try and deploy it yourself. So one of the first things you're going to deal with when you go through, maybe having built a simple model and trying to deploy it with something like Flask, is that you're going to realize real world data is not the same as all the stuff you learned when you were running through tutorials or the examples on tooling websites or whatever. And that actually real data is horrible, right? It's stored in loads of different places. You don't get a nice CSV or a import data set from TensorFlow type function. You have to go and get it from databases. These all might be in different formats. They might be across different places in the organization. And then you have to deal with the actual values in that data. And sometimes you end up with missing values, you end up with inconsistencies, weird data types, etc. As I mentioned, the kind of the schemas could be off. You have different data formats depending on the different source that you're using. And then you go through a process called feature engineering, which is how do we take that data? And this is kind of a little bit like a data engineering role. So in the way that a data engineer might design ETL processes and store stuff in a nice reusable data warehouse for reporting or for machine learning or what other use cases. Within machine learning, we have this thing called feature engineering, and that's that. At its simplest form, a machine learning model takes numbers as an input and it gives you a number as an output, right? It's all just maths underneath. But not every piece of data we have is a number, right? If I have a categorical list of, I don't know, let's say I'm an online retailer and it's, product type and it's, t-shirt or jumper or jeans or trainers or whatever, right? How do I can't give that to the machine learning model because it's not numerical. It doesn't know how to then infer relationships on things. So I have to convert that. Something I might do for that would be, really simple, go down the categorical list and just assign it an integer. And then each of those becomes like the index that we can look up in, a dictionary somewhere. That would be a really, really simple example of feature engineering. And often this process that a data engineer or data scientist goes through can be quite complex. For example, with when I'm looking at natural language processing, taking large documents of text, normally what we do is we break those down into things called word embeddings, which are like a numerical representation of the word or the sentence that contains some sort of semantic meaning and context of where it was in the sentence and stuff like that. And this piece of work is something that I'm highlighting now because I'm going to talk a little bit later about how we can reuse some of this effort that goes into it. And then another challenge you'll start to see as you deploy your very simple Flask app is that actually not all deployment modes are the same. So yes, you get these like online predictions and your REST API is fine, right? It can receive a request, does a prediction, sends a response. Nice. But actually, how well does it handle batch workloads, right? If we look at things like recommender systems for websites, most of those are run as a batch job, maybe at the end of every day or overnight, so that when users log in to an e-commerce site in the morning, they have the recommendations already there and served and ready. That is the kind of thing that they might be running across millions of users. So now you're suddenly asking your API to do 1 million predictions all at once. Pretty sure it's going to fall over. So how do you handle batch workloads? That becomes another thing. And then streaming and low latency applications of it. So particularly we see this a lot in the live video domain, being able to do object detection on video frames as they come in. For that, you need to be incredibly low latency. You need to be able to run predictions on every single frame of every image, or near enough, and be able to provide the response almost instantaneously. So suddenly you end up with these different deployment modes. On top of this, like machine learning models themselves, the actual artifact can be really, really huge. If you look at some of the popular models nowadays that you can get pre-trained and download, things like GPT-2, that's a really good example in the natural language processing space. That model itself, right, if you download the full thing, is something like 60 gigabytes, I want to say. And some of them are in the hundreds of gigabytes, right? Some of these big, billion parameter models. That actually becomes like a DevOps challenge. It's like, how do we pull that thing down, store it on a machine somewhere, have enough memory requirements on the machine, or whether I'm running it on, for that kind of use case with billions of parameters, it's going to be very slow doing inference on a CPU. So you probably want to allocate some GPU resources to that. Suddenly you end up with these kind of bespoke infrastructure requirements. And then some even more like complex scenarios you're going to hit is that not every model just gets deployed as a standard unit, right, on its own. Some of them are like combinations of models. Maybe if I'm doing a classification problem where, like, let's stick with the example where I'm an insurer and I have, people upload images of the crash, right? When they get in a crash in their car or their motorcycle or whatever, they'll send me an image. Now, the first thing I might want to do is run a broad classification to figure out whether the vehicle involved is a van, a truck, a lorry, a motorcycle, a bicycle, whatever it is, right? And then having done that, if I get the result back says, oh yeah, it was a motorcycle, well, now I want to pass that to a classifier that then identifies what type of damage it is on a motorcycle. Is it that the handlebars have been damaged, or is it tire damage, those kind of things, and that might be a bespoke model specifically for motorcycles. So in that situation, you end up with like a combination, a hierarchy of models, and all of that needs to be contained within the deployment so that the end user can just send a request to the API and get the response back that is, the motorcycle has damaged handlebars. But in terms of how we do it under the covers, there are some complexities that we need to manage. And then, another example is like transformers. This is a very frequent one we see and this goes back to why I explained feature engineering and how everything has to be a mathematical representation in order to be fed into a model. Is that if I'm doing, some like analysis on like some written text, right? That text needs to be converted into word embeddings. Then those are passed to the model, and then the model itself will give you maybe a numerical representation back. And then I have to convert that back into words if I was going to do, let's say, language translation. Now, that means I need an input transformer at the front. So I need to do some transformation. I need to run the model. And they also need to be able to run some transformation and some logic on the output as well. And again, all of that needs to be like deployed alongside the models so that the predictions can just be sent, and I can send text as my request, and I can get text back as my response. Okay, the good news is that like a lot of these challenges that we're facing are not new. The ability to do streaming workloads and batch workflows and things like that. These are things we've seen in DevOps for years, and Kubernetes now is the pretty much de facto standard that people deploy containerized workloads on. Solves a lot of these challenges and allows us like flexibility in the way that we do things. So at Selden, we have pretty much standardized everything on Kubernetes. That's how we do everything, and that's actually what we've done is built a bunch of open source tools that run on top of Kubernetes that help you tackle a lot of these problems. So the first and most important of these, I think, is Selden Core. Now, what does Selden Core do? Okay, so at its highest level, I say it deploys and monitors models on Kubernetes, right? So I have a machine learning model. I want to run it on Kubernetes. Like, go and use Seldon Core, because the reason we built this library, right, was actually that, interestingly, the company did not set out to build tools. We set out to do some natural language processing in the fintech space. And the more that the company started working in that, the more we realized, like, oh, we have these really horrible deployment challenges. It's really hard to build a model that scales. We knew at that point we wanted to use Kubernetes, but there wasn't anything around. So we ended up building our own operator for it. People started showing interest, and we said, you know what, let's open source it. And actually now the whole company has pivoted, and now we provide tools. But at the heart of it was this Seldon Core open source project that came out of a real use case and challenge of being able to run these models at scale on Kubernetes. So that's basically at the highest level what it does. If we go down a little bit further, we see that what it actually does is it containerizes the model and then serves that out over a REST and gRPC interface. So it's these nice little microservices. It also does some routing over the top. We'll talk about that in a second. And the other thing it provides are these highly optimized inference servers. So depending on whether your machine learning model is maybe a TensorFlow model or a PyTorch model or scikit-learn or whatever, right? These are all different machine learning frameworks that your data scientists might use to build the model. We build these inference servers that are optimized for the exact workload. So the scikit-learn server will run the scikit-learn models for you. The TensorFlow server runs the TensorFlow models, etc. You don't really have to worry about that underneath, right? You just kind of say, here's my model, go and run it. It's a TensorFlow model. Okay, so what does that look like? For the kind of Cube enthusiasts, we have the Seldon controller, which creates the objects in there for the CRD. And it also creates the appropriate ingress rules so that it can route to the deployments that we create underneath. And then we have this custom resource definition called a Seldon deployment. And that is very much how people define a model deployment on Kubernetes. And I don't know if this is visible to people depending on how high your resolution is and what monitor you're watching on, but you can see down here, actually, this one has implementations sklearn server. So it's using the scikit-learn server. And then we've provided a model URI there, which is basically saying, here's where my model's stored. Please go and get it and pull it down and then run it on the inference server. Cool. So I'm just going to take a sip of water very quick. Okay, so one of the nice things about running on Kubernetes is that we can then integrate with all the tools that people already have and love and use. And it means we don't have to build features for all sorts of other aspects of the deployment that we're going to need to do. So, for example, if you want to log every request and response, you can do that. And we use Elasticsearch, and there's an integration we built for that, which makes it really easy. If you want to do distributed tracing across all of your models and understand exactly what does the latency look like, from when I send a request on my machine or from some other app, let's say my model, returns after 2 seconds, I get a response and I get my prediction. That's great, but I don't know what's causing the delay in there. Is it the actual model inference? Maybe there's some networking, it takes time to jump from, my machine to the actual cloud kube cluster or whatever. And then maybe the ingress takes time. Maybe the transformer step is the bottleneck. Using something like Jaeger and open tracing, you can see all of these network hops, which is really cool. And you can see exactly what takes the time. So it's really handy for debugging low latency stuff. And then, metrics pretty much pretty much everyone we speak to who uses Kubernetes uses Prometheus for handling metrics. So, as you deploy your models, if there's a Prometheus server on your cluster, we automatically scrape metrics and send them to the Prometheus server for you, so you can then visualize them with tools like Grafana. We integrate with things like Knative and Kafka for stream processing. Again, we see tons of people using Kafka for pub sub type workloads, and being able to run predictions off the back of those is actually a really common use case. So yeah, we have integrations to those. And then finally, there's to do those big batch processing, you can use workflow managers like Argo or Airflow or whatever. But we also provide a CLI, which will distribute batches and scale up deployments automatically for you on your Kube cluster. If you want to run large batch workloads manually, you can do that too. So yeah, that's some of the cool stuff, right? And that's kind of not an exhaustive list, because the great thing is being a part of the Kubernetes and CNCF ecosystem means that we can swap and add extra integrations in and out as and when we need them. Okay, so we've kind of got over the DevOpsy side of things, right? Deploying a model, yes, there are lots of challenges, but we can solve a lot of them with Seldon Core and Kubernetes. But ML deployments are not just code, right? We talked a little bit about the file sizes that they can be, but we need to store those files somewhere. So this is more talking about the overall MLOps processes that we have to understand. And increasingly, I would say to people, if you don't have a model registry, get one, right? Some people just stick things in an S3 bucket, and that's absolutely fine for storage, but you should probably use a tool over the top that tracks which version of a model has been stored where and metadata around it, because then you end up with this. So I'll talk a little bit about inference metadata in a second, but you want to be able to know when was this model trained, what was the code used to train this model, what was the data used within that run, etc. So that the dream is to be able to say, I've done a prediction, right? Here's why your let's stick with the insurance example. Here's why your claim request has been rejected. So you've been rejected, but you can then trace it all the way down the stack, and you can say, well, we made this prediction because we were serving this version of this model on this infrastructure at this time, which was trained using this data and this set of hyperparameters and so on, right? So you end up with this provenance and audit trail all the way back to the actual data, because ultimately that's what's happening with machine learning. You start with a load of data, you're using that to generate a bunch of rules, and then you're going to make predictions with those rules. So people often want to know, well, when you make that decision, why did you make that decision? And you can go all the way back and say, well, we made it because of this data set over here that maybe we collected for 3 years worth of claims on people similar to you, right? And that's why we've rejected this one. So yeah, I talked about metadata. That's really important, but you also need it on, particularly on deployments, right? For things like the inputs and outputs of models are not always the same. In the same way that we're familiar with working with REST APIs and them having a nice API documentation. First thing we do is go and read the API reference, right? Whenever we want to work with something, because you don't know what the server expects and what it's going to respond with. It's the same for a machine learning model. The inputs are different, the outputs look different. There are different schemas they might have to follow when sending a request, etc. And then increasingly, we're seeing people interested in building things called feature stores. These are essentially a way to reuse. When I talked about feature engineering and I said, we have to convert everything into a numerical format so that machine learning can make use of it. Feature stores are a way to kind of store that and reuse it. So a really, really simple example might be, my data for all of my customer transactions just has a timestamp on it. But timestamp alone is not very helpful for training a model. Maybe I want to actually know what day of the week is it? Is it Saturday morning or not, right? I might just do some very simple feature engineering, and I'll now have a column that says, is it Saturday morning or not, 1 or 0? Perfect, right? I've done that work. Why should someone else in my department or in my company ever have to do that work again, right? Why can't I just store it alongside the data in a feature store, and then other people can reuse it? So it allows this reuse, and it also allows for sometimes, people might say, make a prediction for this customer, and they just give you a customer ID, and you need to go and retrieve a bunch of features for that customer. So you might do like online data collection for stuff, and feature stores tend to be very low latency, so they're a good way of doing that. And I talked about data provenance already, being able to trace from a prediction all the way back to the original data that was used to train a model, being very important, and particularly in more heavily audited industries, we're seeing like that become a real priority. Okay, so talked about some of the issues, but all of this needs to be automated, tracked, versioned, etc. Right? We know all this because we're from DevOps and cloud backgrounds, but data scientists definitely don't, so they need our help, right, while doing this. A couple of cool things that we do at Selden. So we are big fans of like GitOps as an approach. All of those Selden deployment custom resource definitions that you saw, so the Selden deployment objects that we create, the manifest gets stored in Git, and then we use Argo to automatically sync those to the cluster so that we have like full recoverability, an audit trail. We can roll something back if it goes wrong. If the whole cluster dies, we can spin the whole thing up on a different cloud provider within minutes. It just gives us a ton of auditability and fault tolerance. And then something else we do that's really cool, there's a project called Iterate from IBM, and we work with that to use to do progressive rollouts of models. So maybe I've trained 3 different models and they all look quite good in my like internal tests, but I don't know how well they're going to perform in production. What I might do is roll them out and say, split traffic across them like an A/B test, but monitor them for a certain metric. So it might be, how accurate these predictions it's making. How many times does it get one right? And then over time, I want you to start sending more and more traffic to the best performing model. And eventually you end up with, one candidate wins out over the others. And you can say, model B is the one that's being promoted to be my production model, and the other candidates can get discarded. So that's quite a cool thing that we do that allows you to roll things out in your production workspace. And then on top of the kind of, generic infrastructure monitoring and application monitoring that you'd expect, machine learning has some other nuances that you need to monitor for. So the first of these is drift. And I think the best example for this is to just, well, actually, do you know what? Before I give an example, I'll explain. The reason drift occurs, right, is that machine learning models, more often than not, try to predict real world phenomena. Anything in the real world typically involves humans, and humans are a nightmare because we change all the time. We change our behavior. We're not even all like, none of us live forever as well. So we're kind of ephemeral, I guess. We disappear, people's buying patterns change, etc. So all the kind of things we try and predict tend to change. And what happens is, as let's say, your buying behavior changes, your machine learning model that you've used to predict, whether something might get bought or sold, goes out of date. It becomes stale. Best example of this I can give is, let's say you've trained a house price prediction model. You can give it the number of bedrooms, where it is, how big the garden is, etc. Tons of different features, and it tells you very accurately what the price of your house should be and what it will fetch on the market. And then something like a pandemic happens, and suddenly people don't want to live in, I live in central London, so people don't want to live in central London anymore. They want to move out, they want to live in the countryside. They want spare rooms because they have to work from home. They want outdoor space. It changes the buying behavior, which means our model no longer accurately gives anyone a good valuation on their house. So maybe we need to go and gather more data and retrain. So we have to be monitoring for this continuously. And there are a bunch of different algorithms you can use. Other things we might want to look for are outliers. So, if let's say I'm approving loans automatically based on a machine learning model, maybe one comes in that looks like it should be approved because it's, they are asking for, 10 million euros, but their salary is like 5 million euros a year. So in theory, it looks like maybe we should give that one. But because the numbers are so statistically different from what we're used to seeing, maybe we just flag that as an outlier and say, let's do some manual intervention. And then finally, you might want to monitor for adversarial attacks. There have been some really cool research papers that have shown that, by adding stickers to stop signs, for example, you can trick self-driving cars into not stopping. So you need to be monitoring for these kind of things in your machine learning models to try and stop them before they end up affecting your systems. The good news is, again, we've had this problem already, right? We see it all the time. And so we built another open source library. This one is a data science Python library called Alibi Detect. It does drift, outlier, and adversarial detection. You can use it standalone as just a Python library, or you can use it to deploy monitoring on top of your Kubernetes models that you've deployed with something like Seldon Core. And if that wasn't enough, right, there are still more headaches. Trust me, I'm getting towards the end, but we, a few more things that we need to consider. So I haven't really talked about training at all, but the actual machine learning training part, which is where you give it tons and tons of data and you say, go and figure out the best set of algorithms that will make good predictions. And it does, thousands and thousands of iterations of trial and error to try and get good, to infer good relationships between the data and the output. That is really resource intensive, requires more often than not, lots of GPUs, sometimes has to be distributed across multiple GPUs, and you might spin up lots of different training jobs and then have candidates die off as they don't look to be performing well, etc. So that's definitely like a headache. Definitely something to look at. There are lots of tools in the space that will do distributed training and experiment tracking. Testing, I said it was pretty much non-existent in what I've seen in data science, but we need to convince the data scientists to do more. If you're writing Python code, you should be writing tests for it as well. Anything that's at least somewhat mathematical should be tested. It's harder when things are very probabilistic and we can't be sure, but a lot of the code can be tested, and we should be writing code tests for it. We also have the model evaluation stage, which is kind of like testing, but these are kind of mathematical tests against the actual model to know how well it's performed. So, we might have accuracy is one that everyone can understand. It's kind of like, how many times they get it right, how many times they get it wrong over the total number of times it got right. So if it's 97% accurate, you'd expect 97% of the time it predicts the right outcome. But that doesn't work for what's a model that translates French to English. And what's the accuracy number mean? Well, it doesn't really mean anything, right? So we have something called a word error rate, which might tell you, how many words from the source language did it not have a reasonable representation for in the output language. And again, that's hard to measure, right? Because you've got to go and either have humans test it, or you've got to have the actual agreed upon translation of that sentence and have some sort of consensus on it. And then we often actually need to optimize these models for the destination hardware. So depending on, if we're deploying them on GPUs particularly, there are some cool tools like Apache TVM that will compile your model for the destination hardware and make it run a lot more efficiently. And then the final thing people are going to start to moan at you about is once all of that's done and you've kind of got the perfect MLOps stack, you're going to have an annoying customer who's going to come back and say, yeah, I'm not cool with you just telling me that the computer's just predicted that. So I want you to explain why it's predicted it. And so there's this whole kind of science around it. There are two different ways we can look at it. The first is, can we attempt to explain how the whole model makes predictions? And the second is, well, for an individual prediction, let's have a look at why that individual prediction was made. And there's this whole data science field around it. Again, what we did was we built another open source library for it. So there's Alibi Explain. another Python library, can be used standalone for explainability, but it has both techniques for white box and black box. So what a white box explainer is one that has access to the actual model architecture. It can read the weights and understands how the model has been trained. A black box model is kind of as you'd expect, right? I have no information about this model. All I can do is send requests, get responses. I'm going to have to do some sort of interrogation to try and understand how it makes predictions. And actually, if you think about explainability, right, that's the kind of thing we do all the time. I'm sure all of you have had to renew your car insurance, and you've gone on and you've put it in. It's gone, whoa, hang on, why is it going to be twice as much as it was last year? And so you try manipulating things. You go, but what if I say, put my wife as the main driver and I put myself as the second driver? Maybe that will bring the premium down. And so you're trying different combinations of things to see how it affects the output. And that's basically what explainability algorithms do. They will try altering the input and seeing how it affects the output. And if you do this enough times, you can build up some statistical significance that tells you, that, for example, my insurance for my motor vehicle is actually, much more expensive, mostly because I moved house and now I live in a more dangerous area of London or whatever it is. So we talked about global and local views, and then it does this for classification and regression models. So again, something to check out if you're looking at trying to deploy explainability alongside the models. And again, something that I would urge people to do just from an ethical standpoint, right? Particularly when you're doing machine learning that makes people's decisions that could change people's lives. If you're approving someone's mortgage, or you're diagnosing them whether they have cancer or not, right? Those are hugely important, life-changing decisions where AI is involved. If you have explainability, you at least have some accountability to say, like, here's why the model has made those predictions. Whether you surface that to your users or not is up to you. But in terms of having it for internal audits, I think it's incredibly important, because it can also often identify where you have biases in your models. Let's say it shows actually the reason, the biggest reason this person can't have a mortgage is because of their surname, right? Why has the model been trained on surname, right? That should be asking you questions like, is my model inherently racist because it's picking up people's names and trying to predict things based on that? We don't know, right? It often gives you an entry point to go and investigate further. Okay, so that's been a hell of a lot to take in. I appreciate, that's just kind of my view on it, but you don't just have to take my word, right? Here's a nice MLOps landscape. This was put together in 2021 by a guy called Matt Turk, which kind of shows you all the different tools, vendors, capabilities within MLOps, right? And you can realize, like, it is a mess. There's tons of stuff to do. But if you can, if you focus in on a lot of the things I mentioned in this talk and get deployment particularly with monitoring alongside it, and ideally explainability if you have those workloads, then I think you get a hell of a long way to being able to do things in a really nice, reproducible and safe way. So what I'll do is I'll end there and say thank you very much for listening. That's as I said, a lot of information, but I'm sure there'll be questions. So either stick them in the chat, or you can reach out to me on email or tweet me or hit me up on LinkedIn. Thank you very much. Kevin, I can't hear you.
Oh, I'm sorry.
Okay,
Not bad. So by the time our listeners put the questions in the Q&A section, I'm going to ask some of the questions that came into my mind.
Okay.
One of those questions which I had was regarding the examples you said, the insurance company or the company which does the housing prices prediction. So when it comes to MLOps, my understanding is we try to make the operations better, more efficient using machine learning algorithms. And often with deployments or testing, we do not have that much of label data available inside the company, that each outliers or would drastically affect our predictions of the models. So, what's your take on what's your take on that, and how do we retrain the model often so that we get a better ops using ML?
Okay, so the issue of not having labeled data is huge, right? A lot of companies struggles with this, and this goes right back to the beginning of the talk where I said, because we don't do data science in an agile way, right? It means that problem is like amplified, right? What I would argue instead is train something really basic. Label some data yourself if you have to, or there are data labeling companies who can outsource things. Get some of the way there. Train something simple, but get it out there and then deploy it, right? Because as soon as you get some users using it, and if you're logging requests and responses, and particularly if you can log feedback from those users as to whether they found the prediction useful or whether it was correct or not, now you're starting to build up a real set of like live data, and there's no substitute for live data in terms of training machine learning models in the real world. So yeah, get it out as soon as possible, get it in the hands of users, and ask them to provide feedback if they can.
Especially in case of operations, our users would be our own operations team in inside a company, especially when it comes to ML ops itself. So my thought was, like, I'll give you an example of testing. So when you're trying to deploy, often as DevOps principles states, we would definitely need to go with the test automation pipeline, and test automation pipeline would require us to have a frequent, like a automated testing pipeline would throw us errors, and we probably need to analyze those errors, and ML ops can be used to analyze those errors to predict which team might have created the bug and try to fix it. So in this cases of labeling those data takes a longer time, and we probably wouldn't be able to outsource those, because it's a sensitive company data that we're trying to label. So how do we go with similar situations?
Okay, so first thing to mention is that this is again the problem with buzzwords, right? Is that there's a bit of a confusion between what AI ops is and what ML ops is, right? So I mean, because they sound like they should be the same thing, right? Typically, AI ops is used to mean the application of artificial intelligence or machine learning on top of operations. So DevOps processes, and the example you gave was great. Looking through logs, etc. ML ops or machine learning operations is typically used to describe the processes and automations that are put in place in order to get machine learning models from design all the way up into production. So very much DevOps for machine learning rather than machine learning for operations. That said, in your example, I think the best thing you do there is buy tools, right? So a lot of the operations tools now have AI ops type capabilities built in, and the great thing they have is that they have the benefit of going out and labeling that across tens or hundreds of thousands of customers, right? And they've probably seen logs very similar to yours before already and done the classification. So that's kind of one of the values of buying a tool that does that rather than building it yourself. So yeah, I'd say that's probably the best approach for AI ops type things, unless you're really doing stuff at scale or it's particularly niche.
Wonderful. So we are running out of time right now. Thank you for the clarifications, and thank you for your session itself. It was wonderful. We went through a lot of topics, and I want to remind the audience that since we had a info packed session here, if you want to go back and listen to the recording, the recordings of the session will be shared in your email soon after DevOps Pro conference this year. So thank you, Shee, and thank you for joining us. I hope you have a wonderful rest of the conference. Have a great day.
Cool. Thank you very much. Cheers.